Manipulatives are a fundamental way of learning regardless of age. Junior high school students are particularly needy in this regard since there is a major change in direction regarding the curriculum. Manipulatives involve students. They create a hand and eye coordination. They motivate the student. They exist to increase depth of perception. Math taught mechanically as a drill and practice methodology seems to decrease the meaning of math. In contrast, real-world math has that type of feeling given to the student that he or she has a grasp on how things operate in the world. Junior high mathematics can be a stepping stone for many students. Students need explanations of the mechanical use of numbers which they spent so many years memorizing and drilling. Students need the tools to expand their concepts of mathematical horizons. Manipulatives lead to multiplistic approaches where students can find answers which are their own and yet work inside the system. Trial and success, not trial and error. Manipulatives support and increase attention. Manipulatives teach the student the big picture when learning all the intricacies in math. They teach the whys and the hows. Math is no longer a chalkboard and a pencil. Knowing these tools, students delve into deeper mathematics now with this sense of ownership. For all types of students, manipulatives are effective. For slower students, it provides time for comprehension. For faster students, it propels them to new planes. Discovery learning is the vehicle used with manipulatives. Thus, students are able to unveil facts which may have had to be revealed in a teacher-directed lesson. The multiplistic approach may be used, giving students a wider field of vision in mathematics.
And they should face like this, so that the loose flaps are on the upper right-hand corner. So the parallelograms, the two parallelograms are facing the same way, like that. Your orientation should be in this position. Now, take this one, take the one on the right, and turn it 45 degrees clockwise like this. Insert it into the other one like that, between the two flaps. Between the two flaps. Right? Now you should be able to do this with it. Now, this is one link. The way you make the link hold so that it doesn't fall apart is you have to take these two flaps, and this is the hard part. They must be tucked like this, in between, and it must be pressed really firmly. Then take the other one and tuck it inside, so you end up with both flaps on the inside. Take it and press it really firmly. The firmer you press it, the easier it's going to slide. Now you have, it will not fall off, and you have one link. And you should be able to slide it, so test it as you do it. Test it to make sure it slides nice and easily. You should end up with your last flap. The last one that you put on your flap should be hanging out. You can test it, and if it moves, you did it correctly. Yes.
We got a triangle.
Yes! Yes! Dan, you gotta rearrange them because they have to be alternated.
That means you have a double fold that will never hold right.
Wait, I think I see what
These are dual.
Oh, look at this. It's got a pattern. Very nice one. Once you get it made, hello? Once you get it made, try and make all the figures. The parallelogram, the square, the rhombus, the hexagon, and the octagon.
After working on these sliding origami polygons, students create a link of understanding between transformation geometry and tessellations. Escher was the master of tessellations, and the following clip demonstrates his artistry.
It is in these pictures of the Alhambra. What Escher didn't like in these mosaics was all these pieces of mosaic, well, they didn't mean a thing to him. He wanted to make mosaics, tessellations, with figures that one could recognize as living figures. And this was really an old interest of him that started much more for this, because actually one of his first blocks is this one, in which you see also a repetition. You have to look a little carefully how many heads there are. 1, 2, 3, 4, 5, 6, 7, 8 in total. 8 different heads, female and male, and looking up and looking down, and all fitting together. So, but his interest in structure, in fitting of patterns was, when you look at it, already present in his first work. For example, here, there is actually this pronounced interest in the tessellation of the cobblestones in the street, and the roof, and the houses, and everything. So, for example, here you have one of his tessellations, and it is a very complicated one, by the way. You see it has some sort of fourfold symmetry, and the real symmetry right in the middle of the figure, where you can turn this around and have 1, 2, 3, 4.
We start by noticing that if I turn this elementary structure around this point, I end up by reconstructing exactly the same design. And if I turn it once more, I end up with another piece of the design. Another thing I can do is to reflect around these axes, and from this image get this other one that I didn't get by rotating previously, and so on. In other words, with respect to these points, I have a rotating symmetry of the third order.
Naturally, Escher was also interested in solid geometric figures in space. Bruno Ernst tells us how Escher chose one of these in particular for a very precise purpose.
Als Escher een opdracht aanvaarde, dan was het meestal een teruggrijpen.
When Escher accepted a commission, he always used a theme he had already used in his free work. This was quite common, of course. For the people who ordered something, preferred to have it à la mode d'Escher. That is to say, something of the ideas they knew from him.
Altijd teruggrijpen naar het werk van vroeger.
When, for example, the Verbliefer, which manufactured cans, etc., for the celebration of their 75th anniversary, ordered an Escher candy box, Escher used a motive that had always interested him. He tried out several possibilities of the regular platonic solids. The tetrahedron was too difficult to open. Was it possible to picture on it a regular tessellation with fishes? First he tried with this solid, then with the cube. That was possible. You see that he sketched some birds on it. But this was too simple. Not interesting.
Kunnen het proberen met het volgende regelmatige lichaam? Ook hier zijn een heleboel mogelijkheden op.
We can try with the other solid, the octahedron. Also here, there are many possibilities. A continuous stream of figures. We can also take the icosahedron. And this comes a little to life. You see that he sketched around it. And last, we have the dodecahedron. What was his final decision? Look for yourself at this row of models. Which would you choose as a candy box? I'll show you what Escher chose. It is this funny box, an icosahedron covered with seashells and starfishes. But it is a box. You can open it and put things in it.
These student creations are based on Escher-like tessellations. Coordinate geometry, Euclidean geometry, and transformation geometry are studied in depth in the 8th grade. The following 3 projects include the study of rotations, reflections, dilations, and translations. Students are expected to show competency with each type of the transformation. First they use dot paper and then plain unruled paper as they work with sliding right triangles, rulers, compasses, and protractors. Mastering these tools is fundamental to all the concepts in Euclidean geometry which follow. Learning about points, lines, and vectors in 2 dimensions creates the groundwork needed to study tessellations. This work incorporates regular, semi-regular, and demi-regular shapes as well as many variations of overlapping patterns using midpoints of quadrilaterals and polygons, as well as centroids. These 2-dimensional studies include Escher-like drawing tessellations.